speaker is Dr. Bob Baxley. Dr. Baxley is the chief engineer at Bastille, where he helps build systems to sift through massive amounts of radio frequency data. He joined Bastille in 2014, shortly after the company was founded. In addition to setting organization-wide technical strategy at Bastille, Bob also leads the data science and signal processing teams. Bob has more than 10 years of experience implementing machine learning systems with an emphasis on cognitive radios. Prior to joining, Bob was the director of the Software-Defined Radio Lab at the Georgia Tech Research Institute. In that role, Bob led GTRI's team to second place out of 90 international competitors in the DARPA Spectrum Challenge. In 2008, Bob earned his Ph.D. degree in electrical engineering from Georgia Tech. During his graduate work, he was recognized with the Sigma Xi Best Thesis Award, the CSIP PhD Research Award, and the NSF GRFP Award. He has co-authored over 80 peer-reviewed papers, is the inventor of 17 patents, and formerly served as the associate editor for the Digital Signal Processing. Please welcome Dr. Bob Baxley.
Thanks. Hello. All right, thank you so much. I'm happy to be here. So today I'm going to talk about a kind of a side project I did where I participated in a Kaggle competition for speech recognition. I'm a little bit of a programming competition junkie, so this was my fix last winter. This is part of a longer talk. If you want to see the notebooks, and there's a lot more depth to it, you can go to my GitHub, and I've got some notebooks and whatnot that cover some of the things I'm going to show today. So let me first give you some reference for what the problem was. So Kaggle had this. Everybody familiar with Kaggle? It's a data science competition website. They had a speech recognition challenge. And the objective was to be able to classify the words spoken in a 1-second WAV file. So the setup was you get 60,000 1-second WAV files. Each WAV file had 16,000 samples. So you have a 16,000 element vector, and you're trying to classify what word was said. So 16,000 training labeled data rows, and there was 158,000 WAV files in the test data set. And you basically make your classifications, and then you get scored. So there's 32 different words. Here I've printed the value counts of the words in the data set. And the measurement metric was multi-class accuracy. Of the 32 words they provide you in the labeled data set, there were 10 words they cared about. So these 10 words, and then silence. So some of the WAV files were just quiet, silence, or noise. And then every other word you were supposed to group into this category called unknown. So the first, the first tip, I'm going to go through and give you some of the tips I picked up in this and I've picked up in my career. One of the first tips in any machine learning data science problem is to understand your data. And one element of that is understanding how your data has been collected. In this case, Google has this really cool open source data recording project. This is the terms and conditions page. If you Google AIY projects, speech recognition, you'll get to this. And how it's set up is this really slick web UI where they present a word that you're supposed to speak. You have to speak 135 words in order for the data set, your data recording, to be contributed to the community. And every 1 second, you speak a word 1 second out of every 3 seconds. So this is interesting for the competition because this tells me how these WAV files are generated. It tells me kind of the error states that are possible, and it tells me what kind of maybe background noise I may be experiencing. So the gist is people are recording these utterances on their consumer microphones. And since you're saying a word every second and these words are changing, it's easy to get tripped up and say the wrong word, or to say the word early so that the word gets clipped, or to say it late so that you miss the end of the word. So after you understand how your data is collected, the next step is to understand what the data looks like. So what I've plotted here is the time domain representation and a spectrogram of 7 samples of one of the words in the data set. So
Sheila.
Sheila.
Sheila. Sheila.
Sheila.
Sheila.
Shay.
So we already heard one of the error states. So down in this sample, we didn't get the la, right? What's really encouraging about this plot, though, is that just visually, even without hearing the words, you can tell what's going on, right? We hear sh, and we kind of see it consistently. We see the 3 phonemes in all the words. The sh is a high-frequency, multi-frequency sound. The E is kind of a tonal sound. And then the L is a long sound. So I found, doing machine learning problems, usually if you can identify the category visually or, looking at it or through some other means, then it's going to be very, very easy for the computer to figure out what the category should be. Let me just play a few more samples from the data set.
No.
Wow.
Bird.
Wow.
Tree.
Go.
0. 3.
Sheila.
On.
7.
2.
3.
On.
Tree.
Up.
5.
Dog.
So there was some trees and threes that were hard to distinguish, even for me, right? At the end of this, it turned out the model that I trained was better at recognizing words than I was, which is kind of humbling. And then we heard some of the noisy and error states. So there was some really distorted noise, maybe someone was speaking too closely to their microphone, that sort of thing. Okay, so another tip when I approach a problem, I look to see what's out there. So if you've got a really hard problem or a problem that you're trying to solve quickly, either at work or in a competition like this, it's usually not a great place to start in the academic literature. Okay, time is of the essence. You don't have time to go reinvent wheels. So the wheel that had already been invented for this kind of problem was computer vision. There's already tons of work out there on computer vision classification, that is recognizing objects and images. So I thought if I can just turn this problem into a computer vision problem, then I'll be on my way. There is speech recognition work out there, but it's less developed in GitHub repositories and that sort of thing. But I can just pull out models like exception and just use those right off the bat for image classification. So my first step of this, the first couple of days of the competition, was just take my WAV files, turn them into spectrograms, classify them with existing computer vision problems, and see how it goes. I was pretty happy with this. If you look at the confusion matrix, so I've taken out the diagonal where the correct states, but you can see there's very few errors. This is the true label word, and this is the predicted label word. So I'm really happy that the validation accuracy is 94%. This is a screenshot of the winning score at the end of the competition. It was 91% accurate. So I thought, wow, this is going to be easy. These guys, day one, I've already got it, right? Well, that's not how it turned out. The public score for my 94% validation accuracy was 77%. I didn't have a bug in my validation code. It's just, it's very rare that your validation data set, even in competitions like this, captures all the nooks and crannies of your data. So a lesson here is internal cross-validation is almost always optimistic. I see this at work all the time where we do other kinds of machine learning problems. And it's very easy to capture a data set, run a model on it, get excellent results, and think that you're done. Usually when you start productionalizing that, you see new nuances to the data that weren't captured in your training set, and thus break your model. So in addition to just being disappointed, I kind of identified some of the issues with this first step. One is it's really slow to use a CPU to make these PNG image files from my WAV files. I hadn't done data augmentation or dropouts or had enough fully connected layers, so these are kind of nuances of the machine learning algorithm or model. And then my spectrograms were really kind of small, 100 by 100 pixels, so I lose a lot of resolution there. So approach two, going back to let's leverage what other people have done. The biggest bottleneck here was it's slow to make PNG files, which means it's hard to do data augmentation. Data augmentation is where I take an existing data sample, an image, I might take an existing image and then mirror it. And so now I have a new row, or I might scale it or pan it or do any of these sort of things. I can do that in voice too by changing the pitch of the sounds, speeding it up or slowing it down. But that ends up being really challenging if you're having to write each one of these to a PNG file. So it'd be great if I could just do that WAV to PNG-like file as part of my model. And it turns out that somebody had gone through the trouble of writing a custom FFT model layer for Keras, which is what I was using, that will use the GPU to do the spectrogram generation. So that was really fantastic. And that made it so that I could automate a lot of these data augmentation steps and really quickly iterate through my grid search. So I've gone from 77% to 85%, still a far cry from the top of the leaderboard. At this point, I've really sunk some time into this. This is a week into December, and I'm getting close to Christmas break, and I don't want to spend all Christmas break on this, but it's hard to break away when you feel like you're making progress. So lesson here, outsource your pre-processing to the GPU whenever possible when you're doing some sort of machine learning problem. Next up, I didn't actually follow through on my first lesson more thoroughly enough. So I started looking at the test data wave files. And I realized that, as you start playing them just like I was playing before, and all of a sudden there's these brand new words that I'd never heard before. So I thought, wow, that's a curveball I hadn't expected. It turns out that they're expecting, and the problem setup was such that they're expecting you to deal with novel words and classify them in this unknown class. So I had 32 words in my training set, but the test data set had many, many more words than that. And if you don't treat that, if you just use, say, the stock computer vision model from like ImageNet, it assumes that everything it sees is in the class vector, right? So I don't have that situation. I've got this unknown class, and I've got new words that are not in my training set. So now I did have to put the academic hat on and dig into the literature a little bit. It turns out there's this really cool loss function that you can apply to your model to deal with unknown data, and it's called a triplet loss function, and it was generated for facial recognition problems. So if I have a facial recognition problem and I only train on a subset of faces in the world, which is a requirement, and I see a novel face, I want to put that in a novel class. I don't want to just associate it with an existing face I've already seen. So the guys and gals at Google came up with a paper on triplet loss function for facial recognition. Just to kind of go into the intuition a little more, the standard multi-class objective function puts every point in my wave space, my input space, into some point in my feature space, and then it draws boundaries. And those boundaries completely span the space, so any point in the space will be in a boundary. Triplet loss forces my points in my feature space into these tight balls. So in this case, if I use a Euclidean distance metric in triplet loss, I get these Euclidean balls. And then I can draw my boundaries around those balls, and a point that might end up in this space over here and behind this boundary now ends up in this kind of no man's land where it will be classified as an unknown in the unknown class. Okay, so that's what triple loss does, and it's really good at that. I'm going to skip the math in the interest of time here. But let me just point out, who's used Keras? Just a couple people, a few people. So it's really, really awesome. It does all the optimization for you. All you do is set up layers. And then once you've set up layers and set up your objective function, you just push go and it does all the things. So creating this triplet loss function was just, a dozen lines of code, which is really incredible to me. And then you're good. And you let it run. Another just kind of quick aside, has anybody used Google's Collaboratory? Okay, so if you haven't used that Google Collaboratory, it's a Jupyter Notebook clone that's hosted by Google on Google's virtual machines. But the really cool thing about it is that you can use a GPU instance for free. So you can get into Keras and heavy-duty machine learning with deep neural networks for free very quickly. Anyway, so after doing all that, now I'm up at 87%, getting better for sure. But this triplet loss training ends up being really slow, and it's really hard because you're doing all these triplet combinatorics. So the second to last approach here was to use a multi-objective model, a loss function in my model. So we'd have these word classes, and I thought, well, if we can also train the model to recognize phonemes, then maybe the model will have some idea of how words are constructed and which words might be novel. It might help the triplet loss function along a little bit. And so here I've got a plot of the 32 word classes. So this is the word 9, and this is 50 rows of 9 being classified. So you can see it's consistently classified as the 13th class, which is the 9 class. You can also see it's caught the N phoneme and the ein phoneme. And then no is mostly correctly classified. And you can see it has a common phoneme, this N sound. So this is just a quick example of, one of the things I took away from this experience was these multi-objective loss functions are really cool for helping you bias your models in a direction, to help them kind of make them aware that there's more out in the space than just the data in the training set. Okay, so in addition to that, I also let the model train a lot longer. It's very easy to get impatient in these Kaggle competitions. So this training, even with a really fancy GPU, it was taking 12 hours, and I let it run for 36 hours. And it turns out that was part of the trick to getting a much higher score here. So now I'm, near the top of the leaderboard. Not at the top of the leaderboard, though. So the last lesson I took away from this experience was, if you can't beat them, join them, right? So Kaggle has this really nice feature where Kaggle's a great website. They're trying to encourage people to learn data science. And part of learning is working on a problem with other people. So I looked ahead of me in the leaderboard and said, these people with 5 of these little gold things are grandmasters. I forget the exact classification, but they're really good at this. So Russ here, I sent Russ a cold email and said, I've got a model that does 89%. Can I join your team? I won't take any of the money. I'm just looking for the experience. And Russ was happy to have me, so I joined Russ's team. We had a Slack channel, and that was a really fantastic experience. Learned a lot from Russ. A lot about things like model stacking and ensembling after you've got good models. And so here's a plot of that. When we all got together, we had a bunch of models that were good. And so this is a cluster map plot of clustering the correlation between the model predictions for various models. And so what we're going to do is take our various models and ensemble them and use the ensemble prediction as our prediction. To do that effectively, you need to understand which models provide diversity on your predictions. So this map kind of tells us that. These models have a lot of similarity, and these models aren't very similar. And then all these models have similar performance, so I'd rather average these models than average 2 of these models. I'll get better performance. So at the end of the day, we ended up at 89%. We're pretty happy with that. And you can see in our notes here, we're just taking 5 models and just done a really simple weighted average. There's some super sophisticated model stacking, ensembling things you can do and that people do in Kaggle competitions. But it turns out the data volume here and the model size was so big that it's hard to do multi-level model stacking. So we just did this simple weighted average ensemble. So at the end of it all, we were in 6th place, which we're really happy with. About 90th percentile on the private leaderboard. So this is what's exposed to you during the competition. After the competition, they rerun your model on rows you've never seen before, and we were a little bit higher in that, which was great. So we're pretty proud of that. We were actually only, a couple hundred classifications away from being on the top. So it was a great experience. It was not very healthy. This is me working basically all nights and weekends through Christmas to my family's chagrin. But I do know a lot more about this stuff now. So a big lesson here. This is actually not a great lesson for production applications. Ensembling really just squeezes out the last couple percentage points. But if you want to win a Kaggle competition or the ImageNet competition, ensembling is key. Just a note on the last point here. So there's a 90-minute version of this talk that I give that has notebooks and live coding and whatnot. And I talk about how the last couple of years, the ImageNet winner has just ensembled a gigantic number of models. So ensembling is key if you want to squeeze out a little bit of extra performance. And that's all I have. Thank you very much for your attention.